All right, so there's a lot happening on my screen, but if I'm not mistaken, I am sharing my slideshow. Is that right? Like someone just chime in the chat. All right, perfect. Thank you. Good, I've got way too many windows open here. Cool, we'll give it a couple more minutes and then we can get started. All right, I'm gonna go ahead and get started. It looks like there's about 80 people here, which is pretty good. Welcome to the first lecture for TDA594, Software Engineering Principles for Complex Systems. If this is not the class you were expecting, well, oops, good luck. In any case, welcome, just a bit of etiquette, etc. Before we get started. We are live streaming and recording this concurrently. Everyone's been muted. If you have questions, please ask them in the chat. I'll be keeping an eye on the chat as we go, and we'll try to respond to questions pretty quickly, just whenever there's natural breakpoints. So this is kind of like a Twitch stream, you know, with maybe slightly less racism. In any case, welcome. So way back in the beginning, software was small. This was something that was true physically. Code was small enough to fit on punch cards, computing power was limited, and we can't really run much. So by necessity, and because of the lack of experience, it was small in scope as well. And software is important. It was really, really crucially important back in the beginning, but focused on particular problems: missile trajectories, simulations, war games, code breaking, single task assignments, no APIs, no code reuse, limited functionality, and no evolution in functionality over time. But it didn't remain that way for very long. Our experience and our computing power grew and matured, and as it did, we started to expand our ideas of what could be done with software. Languages like C let us start linking files together, which allowed us to organize our code, to put our code in logical positions, group with like-minded code, and reuse that code. Languages like Simulus 67 or Smalltalk introduced the ideas of objects, which let us organize our code into these focused units that work with other units of code to perform larger tasks, where sections of our code activate where they're needed, where we can group together related functionality, we can ignore the unrelated functionality, and find what we need when we're making changes to the system. This also enabled code to be reused in future projects. This enabled so much growth in software and what we could do and what we could dream of doing. And now, as we flash toward the present day, our entire society depends on software. That scope has expanded, right? A web page is powered by software. The platform you're watching this lecture on is software. No one's going to dispute that kind of thing. If I were to ask you to just name a piece of software, you'd mention something like this, Zoom, Google Drive, a video game, a word processor. But that's not all that is software. Our society at this point is basically run on software. It powers our homes, it manages our private information, it controls our cars, it automates our factories, it even regulates our bodies. Real world software systems are becoming increasingly complex and increasingly pervasive. So if you think about application domains like enterprise computing, AI systems or data processing, business information systems, web portals, cyber physical systems, your automotive software, your home automation, or your system software, your operating system kernel, or even your mobile software or software ecosystems like the Android OS and its apps, right? These are huge, incredibly complex systems with tons of functionality. And all of those domains boast systems of incredible complexity, and that only keeps growing over time. And many of these systems are long living. Many of these exist in different variants. However, this growth in scope also means growth in the size and complexity of the code base. If we look at most modern systems, many of these have millions of lines of code, not thousands. Many of these have hundreds of classes, if not more. There was a story a year or two back about Facebook's iOS app, and it had 18,000 classes. Now that's not typical, and that was partially a result of automated code generation, but hundreds of classes, that's common, right? And that idea keeps growing, that level of scope. And even then, well, we don't necessarily want to write code once and be done. We want to reuse code, either in our new system, right? Or even make it something that others can make use of too through a common API, right? We want to run that code on different hardware platforms, in different apps, in different versions of the same app with only minor adaptations. We want these systems to last for years and years to come, right? And that's not easy. This level of growth is good. We can do incredible things with software that were impossible before, but that comes at a cost. And there have been some growing pains. No one person can understand an entire million-line code base. Classes are great for organizing code at a small scale, but how do you find the right class when there are 18,000 of them? It's hard to plan for all these circumstances. It's hard to plan for new hardware platforms, right? Or new interfaces, new access methods, new variants of your code base. And this results in chaos, right? These are just, these are figures from one study. Don't take this as the exact gospel truth, but there was a study that found that about 16% of projects were delivered on time and within budget with all the features complete as specified. And then about 31% of projects were just canceled before delivery. The rest of those came out, but were flawed. They might have been late, or they were slow, insecure, missing features. They had duplicate code. They go down often, and et cetera, and so forth. Right, so the key to delivering robust software then is through a thorough design and verification process, right? To design a system that's understandable, that's organized, to verify that the features of that system work as we expect and that they interact as they expect, which is often the bigger problem. In other words, taming the complexity. And that's what this course is about, is taming that complexity of modern systems. Through dedicated planning, modeling, design, realization, and advanced analysis, all of which are needed to deliver these systems in a safe, robust, and secure manner. And we exemplify this largely through examining a type of system known as software product lines. So today our goal is to introduce the course. What is this course? What are we doing it? What the heck is going on here? We'll talk about the course PM. We'll clarify some of the expectations, talk about assignments and so on. And then we'll start to get into some introductory material, some motivation to set the stage on what we mean when we discuss software complexity and how systems designed around reuse and designed for reuse are able to help tame that complexity. Right, so the goal of this course is to present a set of advanced techniques aimed at creating complex systems with many different interacting features and variable configurations. So what we're going to do is we're going to look at the different stages of our life cycle, look at the design, the implementation, and the verification of complex systems, focusing on managing complexity at different stages of the system development lifecycle. We're also going to examine how the development process needs to be organized to deliver these systems. So, we only have about 7 weeks of lectures here, right? And a little longer when you factor in assignments. But, so we can't go over everything, but a few things we're going to focus on include modeling a system and modeling how it can vary, analyzing the models we build of systems, designing systems for modularity, to divide the system into independent units and structure those units together. Looking at design patterns that help us manage complexity and allow evolution of systems. A little bit of API design, a little bit of examining system and feature level testing, and a little bit on automated test generation, right? We could probably devote an entire study period to a handful of these topics alone. So we bits and pieces structured along the life cycle, looking at how we can design systems that are complex and how we can manage that complexity. Now, what the flip does complex mean, right? The word complex, that can mean about anything, right? Almost any piece of software you ever build in any professional setting is going to be complex. Anything you build in the team, anything that's sold commercially, arguably every single class you've ever taken during this degree is preparation for building complex systems. So we need to focus this class in some way. And so our focus is going to be on variability and evolution. Variability is our ability to change and customize software, to choose from a set of options to configure, and evolve software to the needs of new groups of users over time, delivering these customized variants to the users, product domains, and market segments that need them. Variability is not a one and done design decision. It's a conscious process of designing a system for evolution. It requires designing and redesigning systems to be reused and to work with code that you are reusing from your own portfolio of code assets, as well as systems that have been surfaced and microsystems that have been put out by others as well. It requires a constant focus on changeability and maintainability, and our ability to add new options and features to code over time, and our ability to keep existing code still working in the face of constant change. So in this class, this is what we define complexity to mean and what we focus on. Now, much of this course is going to center around a style of development known as software product lines, or SPLs. And software product lines are highly configurable families of systems that are built around common modularized features, assets, portfolios of reusable code. So together, software product lines address the needs of some particular market segment. They're developed from a core set or a common set of core assets in a planned way. And so by developing a large system in this style, building it as a set of reusable assets that you then string together to form a customized system, companies can produce a set of products that are linked together that have commonalities, but that serve independent sets of users or particular customers more economically, since the development effort put into those shared assets doesn't necessarily need to be duplicated, right? We build those once, and then we string them together to form a customized product. This allows sustaining a high rate of product innovation, systems that are highly customized, that can evolve, and that can change over time as needed, while keeping guaranteed levels of overall system performance and quality. Software product lines are seen in many different domains and many types of organizations, and are really hard to build as they have technical, process, organization, and business-related aspects. We're going to talk much more about these, but to give two quick examples, the Android operating system provides a set of core libraries and components that can be tuned to phone manufacturers to a particular device, right? So if you build a Samsung Galaxy S10 and that new Motorola Razr, they look nothing alike. They have different hardware, they have different user interfaces, but they're largely powered by the same software underneath the surface, customized to its particular operating circumstances and even expandable by the user. If you install 5 different apps that can open an email, it's going to ask you what your choice is. It's going to plug in the functionality you request at the right moment based on the right events that occurred. A second comes from a company called Cummins, which is the world's largest manufacturer of diesel engines, and they also make a lot of power generators. They have a core set of software that covers 9 different engine types, ranging from 4 to 18 cylinders and 4 to 164 liters of displacement, with 12 kinds of electronic control modules, 5 kinds of processors, and 10 kinds of fuel systems, right? And so the core software you build is supposed to work in all these different combinations of elements. But they have 20 basic software builds, which have then been deployed into 1,000 separate products based on the same common core assets. And those kind of stories are common. And we'll also dive into software product lines at Volvo, at Boeing, in the Linux kernel, and in many other circumstances. We'll also examine other types of complex systems in this class, largely again built around the core theme of reuse and evolution, and provide some insight into how those are delivered. Right? So why focus on product lines? Well, it's because they're hugely complex systems that are both designed for the reuse of assets. We build independent modularized components that can be selectively integrated. They're also designed to reuse assets, built with a highly evolvable architecture that can easily slot in components. That combination is potent because successful software product lines are highly configurable, easy to tune to their users, but also evolve easily over time. They're hard to get right, but if you nail it, you nail it. Reuse is the name of the game now, regardless of what kind of system you're building. The reality of modern software is that most systems are designed to achieve at least one of those tasks, to either reuse assets successfully or designed to make assets available to be reused in the future. Right? If you use a third-party code library, you are reusing assets. If you build a standalone single-purpose system with a REST API that others can call the functionality of, well, you've designed a system for reuse. If you build an Android app that can be launched by another app to respond to a system event, you built a component for reuse, right? So most modern software is designed either to be reused or to reuse assets or both. Software product lines are designed for both of these. So by examining software product lines in detail, we can teach design and verification techniques that apply to a wide range of complex systems, even if they're not necessarily software product lines in themselves. Design techniques for software product lines are design techniques for any evolvable reuse-driven system. All right, so in this class, we have, of course, a variety of learning outcomes. In terms of knowledge and understanding, our focus is 1, explaining the challenges of engineering complex systems, 2, explaining the industrial practices and examples of complex systems engineering, 3, explaining the processes and concepts for engineering complex and variant-rich systems like software product lines and ecosystem engineering, continuous integration and deployment. 4th, explaining the business architecture, process, and organization-related aspects of engineering complex systems. In terms of the skills and abilities, at the end of this, you should be able to model a system from different perspectives using things like feature models or architecture description languages. So you should be able to engineer a variant-rich system, like a product line or a software ecosystem. You should be able to analyze and re-engineer a complex system, looking at the models of features, analyzing the code, looking at how the software can evolve, looking at how features can interact. You should be able to use and reason about modularization techniques to increase the cohesion and reduce the coupling of software. And you should be able to use modern component or service frameworks. And finally, in terms of judgment and approach, you should be able to analyze existing systems and discuss possible improvements or re-engineering potential of those systems, also taking economic aspects into account. You should be able to reason about the characteristics of software modularity concepts, including component and feature-oriented engineering. You should be able to recognize the situations in which certain of the principles that we teach in class are appropriate to apply and when you should apply those. And more generically, read and analyze scientific literature to kind of look at what the frontiers of research are in these areas and apply those to the systems you build. So hi, I'm Greg. I probably did not mention that before, but I'm the examiner of the course. I'll be teaching most of the lectures for this. I'm the sort of the front line here and the one you'll see most often in the classroom. In addition, Sam Javara will also be providing multiple lectures and has extensive background in software development. So he'll be teaching these lectures from time to time and will be involved with other aspects of the course as well. We have 4 supervisors, all PhD students, who you will be meeting once you start into the assignments a little bit more. And in addition, we'll have a little bit of input from Nicholas Broberry, who's, of course, the program manager for this program. And he's here to help be an interface between you guys, the students, and me, in addition to the course representatives. And also a little bit of input from Thorsten Berger, who taught the class last year. And he's on parental leave now, but he's providing a bit of feedback on aspects of the course as well. Right, so all this information is, of course, on the Canvas page, so feel free to check that as well. Now, of course, this leaves out an important part of the team, which is you, and we need student representatives. What we want is 5 to 6 student representatives. 1 volunteered already, but ideally a few more will volunteer. I think it's better if you're interested in taking on this role. But if we don't get enough within a week or so, then I will choose some random student representatives. But if you're at all interested, please send me an email. We want to fill up these slots, and ideally we want people who are interested in providing feedback on the course, right? And who want to have some kind of impact on the structure of the course and help to right the ship if anything's going wrong. And on that note, feedback is really, really important. And we understand that it can be really hard to get answers to your questions, especially during online courses, especially during the current pandemic. So we recommend the following methods for contacting the teaching staff. If you have questions related to the lectures or assignments, your first stop should be the discussion forum on Canvas. All of us are monitoring this. All of us will come in and answer questions. We'll try and do so in a timely fashion. If you have questions in addition about the group assignments, you also can feel free to email the supervisor who's assigned to your team. And we'll talk more about that shortly. Or email Sam or myself about lecture content as well. You're welcome to do that if it's something that you don't want to post to the discussion forum. If there's anything private or sensitive, please contact me or your supervisors if you want. Right. Course feedback should be presented to the student representatives, as their job is to gather feedback and bring it to us. Right, but if you have anything that's time sensitive, anything that's private, anything that's pressing, you can always feel free to contact me directly. And in general, we very much welcome course feedback. We're happy to adjust elements of the course if there are issues affecting a majority of the students. In general, this is the first course I've taught in this particular program, and really I've only been at Chalmers and GU for a year now, so there's elements of like the Swedish system I'm still learning and getting used to. If there's something that's blatantly obvious I've forgotten, there's a good chance I just don't know about in the first place. So definitely feel free to reach out and let me know if there's something that's just not working, or if there's some common practice I'm missing. I welcome feedback. Don't hesitate to contact us at any time. And if something isn't working, don't wait until the end of the lecture period to tell us, or the study period to tell us. Just let us know and we'll see what we can do about it. Great. Course content in general is going to live in Canvas. All the lectures, files, reading, etc. is going to go there. Announcements will go out in Canvas. Discussions will take place there. We will make pretty heavy use of Canvas, so make sure you are checking that often. There are occasional problems with Canvas. I haven't seen anything yet, but I saw another course where students were just mysteriously dropped this week and then re-added later on. If there's a problem, if you can't access Canvas, if you've been dropped from the course, don't panic, but do send me an email and we'll look into it and get everything fixed. But don't worry, you're not going to lose any grades. We'll make sure everything gets resolved if there's a Canvas problem. Now, I also have a site linked here, this greg4cr.github.io/courses/fall20 TDA594. This is a static backup where we'll put some links to some of the slides and assignments. This is mainly useful if Canvas isn't working and will probably be out of date a lot of the time. But from time to time, I'll put some materials on this page, and it's a good, useful source if there's a problem, right? If something horrible happens in Canvas. There's no mandatory course literature. We've used a lot of materials in preparing the slides. If you check the detailed schedule page on Canvas, you'll even see that we link usually to some related material for the lectures. And this is where you can go if you want to learn more about the topics, see more background material, see more information in general. For every lecture, we'll put up links to a few related resources on it. There are 4 textbooks that we did lean on some for some of the theoretical concepts. This is this feature-oriented software product lines, software product lines in action, the best industrial practices in product line engineering, head-first design patterns, and software testing and analysis, process principles and techniques. All 4 of these books are freely accessible. 3 of those, if you're on the Chalmers IP address, the software and testing and analysis, there is a website you can go to just to get a free copy of the book. All of these are slightly older textbooks, and I'll say that up front. These are referenced for theoretical material that's relevant to the course concepts. In the cases where the books are older, one of these books is actually quite old. What we do is we're using the theoretical ideas that are still relevant to modern systems, but we'll discard outdated theory, and we'll discard outdated technology and update the technological concepts. But in general, we recommend grabbing a copy of all these books, and we'll link to those as they apply throughout the study period. There'll also be some additional optional literature we'll provide for individual topics as well, and we'll link all of that on Canvas. All right, so this is in English, in case you hadn't noticed. Jag pratar bara lite svenska, so we're going to work in English. Trust me, you'll be happier that way. The teaching is going to consist of 2 lectures a week, Tuesday and Thursday from 1:15 to 3 p.m., as well as supervision sessions. These will be once a week, half an hour with mandatory attendance for the supervisions. For the lectures, these are technically optional, but we do highly recommend you come. If possible, try to attend the live stream because you can ask questions easily that way, but we will record most, if not all, of the lectures. There's a handful that we'll need to see if there might be copyrighted materials or things we can't share. But in general, we'll try and announce ahead of time if there's a lecture we won't be recording. But still, definitely you're recommended to attend the lectures so you can ask live questions. The supervision, like I said, formal supervision sessions will be held weekly in conjunction with the project component of the course with your assigned supervisors. This is a chance to ask questions and apply the class concepts, as well as to see demonstrations. And the supervisors will be there to answer questions, At times, the teachers may be there as well, but in general, this will be meeting with your assigned supervisor. The supervision sessions are mandatory, and your supervisor will talk with you to schedule a time slot. All right, so this course has changed some since the last time it was taught. While the core focus has been preserved, many individual aspects of the course have been redesigned. The lecture topics have been revised, new lectures have been added, others have been removed. Slides have been largely created ourselves. In some cases, we'll use some slides from others as well. But in general, lecture topics have been revised quite a bit. The assignments have also been revised. We've streamlined the group and individual assignments. Assignment content has also been substantially revised. And individual examination is going to be performed through a written assignment toward the end of the study period. No oral examination of any kind is going to be given. This is all going to be written examination. Now, the course is examined through an individual written assignment and then a project, which is a series of 5 to 6, probably 5 linked assignments carried out in groups of 6 to 7 students. Each student is responsible to contributing to the group work, even though you're working in a group, and grades in this are individual. So, if you let someone else do all the work, and we will assess this through peer evaluation, then you won't get the same grade, right? So work with your team, don't slack off. Each assignment is equally weighted. Specific requirements for the assignments will be provided on Canvas, along with some idea of what we expect to get particular grades in the assignment, right? The assignments are roughly going to correspond to the order of topics in the lectures, looking at case studies, domain analysis, modeling, implementation, and testing of software product lines. You will also be required to complete self and peer assessments during the course multiple times to help judge the health of the team, to help judge individual contributions to the project. And, as I mentioned, we reserve the right to adjust the grades of a student depending on this evaluation. Now, to give a common product line platform, there's a question, why are the groups so big? 6 to 7 seems like a lot, and that's a matter of resources, to be honest. Like, this is a large class, there's a lot of people. And the assignments themselves are fairly large in scope. So you'll probably find that it's good to have this many people involved. All right, so to give a common product line platform, we're going to focus several of the assignments on this platform called RoboCode. This is a programming game where the goal is to develop a robot battle tank to battle against other tanks in Java or .NET, with a focus mainly on Java in this. The robot battles run in real time and on screen, and a focus in the project will be re-engineering variants of the RoboCode bots, which are themselves kind of interesting systems. They cover different architectural styles and different levels of intelligence, like some incorporate AI or learning techniques, while others follow set heuristics. We'll talk more about RoboCode next class, right? But you can also check out its homepage at robocode.sourceforge.io. All right. So next thing is to talk about is the groups. I haven't really talked about that yet. And really your first stage is to form groups. You may choose your groups. Groups will be, as I mentioned, 6 or 7 people. And what you should do is send me an email, 1 email per group with who's in your group, right? Give me the names of all group members. Now, you don't have to choose a group if you don't know people. If you want to be just placed on a team, you can also email me. These are due Thursday night, right? Come Friday morning, if you've not responded, then I will randomly assign teams from there. But if you want to choose your group, you now have an opportunity to do so. In general, I think groups that know each other tend to work well together, right? So send me an email with your group choice. Do this as soon as you can. Start chatting with each other now and try and get your group submissions in, like I said, by Friday. Anyone who's not responded or anyone who doesn't already have a team will be assigned to a team. All right, now the written assignment portion of the course is going to, the exact format we're still working out. The idea is it's kind of exam-like, but it's not going to be a hall exam. It's going to be a set of open-ended questions largely designed to assess your understanding of the core topics of the course based on the lecture materials. This will be toward the end of the course. We will reveal more details later on. We're still doing some decisions. I see one person in the chat says groups should be 6 to 8 people, so 6 to 7. I'll go and adjust that later on. I think I just missed a reference. The 2 subcourses, the written assignments and the project, are graded individually, both of which have the 3, the 5, and the fail grading scale. There's a question, if you have less than 6 or 7, yeah, you can submit to me a partial group and I will assign more people later on. That's fine, you can go ahead and do that. Try and get as close as you can to the 6 to 7, but if you're close, I'm happy to just go ahead and assign you an additional person later on. All right, so the 2 subcourses are graded 3 through 5 and fail. If you get across the board for the group assignments, what we'll do is we will take the average of the project grades, right? All group and individual assignments need to be submitted. If you don't submit them all, then you don't pass, right? And the final grade, well, okay, as I said, the final grade will be an average of the grade for each of the group assignments. If the average grade is passing, you get a passing grade, right, for the project part of the course, and so on. If you fail one group assignment, that doesn't necessarily mean you'll fail the project part of the course, right? Because you can make this up with the other assignments. Grading is based on assignment-specific rubrics, which will be provided with the assignments. We'll give you some rough idea of what you need to do to achieve each grade. And you'll see that with assignment 1, which I'll put out later this week. All right. Late assignments, 20% off the first day, 40% the second day, and we're not going to take it more than 3 days late. If the final average grade of all the group assignments is failing, then you need to resubmit and redo all the group assignments. Those can be handed in after course completion with a limit of 1 month after the course is over. Of course, you have 2 chances to resubmit an improved version, and the resubmission has to fulfill the original requirements, and for reasons of fairness, you need to provide a detailed change log explaining what went wrong with the first attempt, what you've changed in the second attempt, and what you did to address the feedback you got. Now, just some real quick, just a few minor things in terms of integrity and ethics, right? Submit your own homework for the assignment. This course, of course, has been taught before, and people have shared their homework. The assignments aren't really the same this year, but there are commonalities. But we've kept track of the GitHub repositories people put up from last year, and we will look at those. And if you submit someone else's work, then we are going to fail you, right? Don't collaborate with other teams. Don't use anyone else's work, and be honest, right? In terms of the classroom climates, well, I mean, a lot of this doesn't apply because we're streaming, but some of this is more in person. But in general, don't be a jerk, right? Don't shout obscenities in the chat room. Don't cause a problem. Don't be a disruption, etc. In terms of diversity, right? You're expected to work with all the students. Someday you'll graduate. You'll have to work with a wide variety of people. I don't want to see any issues because of gender, because of sexuality, religion, number of tentacles a person has, anything, right? We have a zero tolerance policy for discrimination, so be nice. And then if you have any special needs, then discuss those with me. That will be kept private, but we'll provide any reasonable accommodations necessary to students who have any kind of special needs. Are there any questions on any aspect of the course PM or what we've talked about so far? Everyone pretty good so far? Cool. Then what we're going to do is we're going to take maybe take a 5-minute break, go grab a coffee, be back at 1:55, and we'll resume then. Right. And if you have questions in the meantime, feel free to send those to the chat. But otherwise, we'll resume in about 5 minutes. All right, that was a fairly short 5 minutes, but let's go ahead and get back into it. We'll take another short break later on if anyone needs. There are some questions in the chat about teams while we were out. The course PM on Canvas did say 6 to 8. What we mean is 6 to 7, and we had just forgotten to update that earlier. So that's been corrected now. So try to keep it to at most 7 people so that other groups don't come short. And then there was a question about how we'll be grading assignments, and that varies from assignment to assignment, but primarily it's the supervisors will develop grading rubrics and will apply those. In some cases, they may use tools to help them grade, but it depends on the nature of the assignment. We will use peer evaluations from time to time to diagnose team problems and look for any issues, and we can adjust grades if there are problems. But the peer evaluations aren't a direct source of grades. They're more used to adjust things after the fact if there are problems. If there's other questions, feel free to keep asking them. Cool, so let's start talking then about some of the actual course material with starting to talk about complexity and variability. And we'll start with a fairy tale. Once upon a time, in the days of old, there was a good software engineer whose customers knew exactly what they wanted. And the good software engineer worked very hard to design this perfect system that would solve all the customers' problems now and for decades and decades to come. And when that perfect system was designed, implemented, and finally deployed, the customers were very, very happy indeed. The maintainer of the system had little to do to keep up the perfect system up and running, and the customers and the maintainers lived happily ever after. That sounds great, doesn't it? But we're kidding ourselves if we think that we can know all the requirements and build the perfect system ahead of time. Software is not a static artifact. It's not a bridge that we can build in place and forget about until we need to go and make repairs to it. The best we can hope for is to build a useful system that will survive long enough to be asked to do something new, and then try and manage that evolution. In particular, there are 2 laws of software evolution that come into play and increase development complexity together. The first of those is the law of continuing change, which is simply that any real-world program, any useful program, has to evolve, or it's going to become progressively less useful in that environment. It might be as simple as the fact that you failed to update the system for a new version of iOS or Android or whatever, and now your app no longer works, right? It might be that we introduce new hardware elements and your app's no longer compatible with those. Or it might just be that people have gotten bored and moved on to a competitor, but in any case, any real system has to evolve to continue meeting the needs of its users. With that comes the law of increasing complexity. As a program evolves, it becomes more complex, and more resources are needed to preserve and simplify that structure. And to see what this looks like in action, what we can do is we can just take a close look at Google. And these are slightly older statistics. These are 2015, but the same trends still continue, if not more accelerated, right? And we can look at the stats as of January 2015. The Google code base, and they all their different products actually live in a single shared repository. And this code base had 1 billion files and 9 million numbers of source files in there, 2 billion lines of code, right? And a 35 million commit version history with 86 terabytes of content and 45,000 commits per workday, right? That's only accelerated since then. But really the important thing to look at is this graph of commits, right? Look at that curve. This is basically an exponential curve. As the system evolves, the complexity of that code, not just its functionality, but the work required to keep it all running, keep it understandable, keep everything from falling apart, increases exponentially as well, right? When we're talking about Google, we're looking at over 30,000 developers and 40 or more than 40 offices all working together with 13,000 more plus projects under active development, right? But they have a single monolithic code tree with mixed language code. All builds come from the source, right? And there are 30,000 commits per day, roughly 1 every 3 seconds, with over 30 sustained code changes per minute, with at times 9-year more code changes per minute at peaks. Half of that code base changes every month. And this requires the execution of over 150 million test cases a day. Now, of course, not everyone is like that, right? But this is not that crazy of a story to look at this level of scope. Now, to look at a major contributor to complexity, we need to step it back in time a bit. Before the Industrial Revolution, the manufacturing process was essentially handcrafting, right? We would knit a sweater from hand, or we'd build parts by hand. And this is a labor-intensive and highly individual process. Everything is designed for the individual customer, whether it's machines, furniture, buildings, sweaters. No two goods are produced exactly the same. And every product was somewhat unique in the sense it was built from scratch. Handcrafting made it easy to incorporate individual requirements to build something that was exactly what your customer wanted, right? After industrialization started, mass production then came in and changed this process dramatically. Mass production based on assembly lines improved productivity greatly. It required standardized parts that are combined to create complex products, right? And so, as I said, this greatly improved productivity compared to handcrafting. The focus on standardized products reduced production costs and improved the quality of the products that came out, which is great, but individualism was lost in the process. It was lost in the sense that the manufacturer incorporates the needs and wishes, or can't really incorporate the needs and wishes of the individual customer. You have one product for all. The early Ford Model T car is the famous example of this, and you could only buy it in black, right? It doesn't matter if you want another color. We only make it in black. Right? Clothing started to come in a set of discrete sizes instead of being tailored to the person buying it. In all these cases, the prices drop and the quality rises, and that's great, but that's at the cost of having only a few standardized products. So recognizing that customers have different needs, manufacturers in the 20th century started to increase diversity in their product portfolios. So car manufacturers started offering different variants of a car at different prices. Right? Manufacturers still used reusable parts, but they combined them in different ways, and they prepared specific alternatives for individual parts, or they added extra parts. This created the idea of a product line. A product line is a set of products in the portfolio of a manufacturer that shared substantial similarities and that are ideally created from a shared set of reusable parts, instead of offering a single standardized product. One size fits all. Manufacturers now aimed at diversification, right? And being able to offer multiple products tailored to the individual market segments, including potential variants even for niche markets, even for cases where you'd only sell a few copies. But because we're building from this shared portfolio of assets, that's not too hard to do, right? So in many domains, mass customization has marked a return to individualism in production. Nowadays, if you make a car, a computer, any number of other products, you can let customers configure the product to your needs before production, right? And so the production process still has the characteristics of mass production. They're constructed at large scale in an automated fashion based on standardized reusable parts. The goal is to share as many parts as possible between all your products. However, manufacturers support variations within the production process, and they allow customers to select from alternatives. For example, different engines, different colors, different interior features, and so on. All right, so customers tailor the product by choosing among a predefined set of configuration options. And often that configuration space is incredibly huge. You could look, for instance, at the Volvo XC90. If you ordered one today, you don't just walk in and say you want this car, you choose your configuration. And almost every car that leaves a modern automobile factory is unique, tailored to the needs and wishes of a particular customer, right? You select your engine. Do you want the traditional combustion engine? Do you want a hybrid or electric engine? Your colors, your gray, white, blue exterior. Do your seats have a leather or a cloth covering? There's many optional add-ons too, right? Do you want a booster seat for your child? Do you want a headrest? Do you want Android built into the display system? You can get all those things added for an additional cost. Those are only a small excerpt to the choices a customer can make. There's often hundreds or even thousands of possible choices when you consider all the different combinations of things the user can select. And this rich set of configuration options gives rise to an astronomical number of possible car variations, right? So the website you walk through guides you through configuration, providing feedback, hiding invalid choices, and so on. It gives choices in terms of checks and radio boxes, and there's sliders, choose from a different spectrum of possible values. Under the hood, those choices lead to more variants than you can really imagine. The BMW X3, for example, right, has 90,000 different roofliner variants when you consider the different choices you can choose, and 3,000 different doors, and 324 different rear axles, right? Coming from different selections of parts, colors, and hardware features. Right? If you consider a simple fuel level indication system in a Scania truck, you'd think this would be simple. Just show me how much fuel I have. But it encompasses around 24,000 different variants arising from combinations of different software features and hardware parts. Some variants are directly related to individual mechatronics components, like your transmission type. Others come from how different parts work together, like fuel efficiency is a byproduct of several different hardware and software components working together. And so what are the kind of numbers we're looking at? Well, 30 years ago in mass production, you'd have only a few variants, select a model and a few extras, right? And, maybe a different cassette player or a roof rack. And one variant, like the Audi 80 with a 1.3 liter engine, 55 horsepower, that was 40% of all sales, right? But now we're looking at mass customization. Now at Audi, you have 10 to 20 different configurations, 10 to 32 different configurations at BMW, right? With 100 different undercarriages, 50 different steering wheel versions. And identical configurations are rarely produced. And that's okay, because once a configuration is set, the corresponding car is not designed and built from scratch, right? It's constructed automatically from reusable parts that are related to the choices they're given to the customer. And this kind of scenario is hardly restricted to cars. Mass customization is a huge part of everyday life. When you order a sandwich at Subway or whatever, you see a product line approach at work. The sandwich shop lets the customer choose among a different set of options and create their own favorite sandwich. And the space of possible choices is actually huge, including different kinds of bread, different side toppings, different meats, different cheeses, different sauces and spices, but it's still finite. The shop doesn't take random requests and shop and prepare ingredients for every order. Instead, they prepare a set of parts, a portfolio of assets, sliced tomatoes, pre-cooked meats, and different sauces and jars, and then combine those. Shared assets, again, the space of possible sandwiches is huge, possibly offering a suitable, tailored choice for the vast majority of customers, but it's still cheap, high quality, and efficient because we use shared assets, right? And if you still aren't convinced, I'm sure most of you have ordered a computer at some point, and when you did so, it's the same deal. You selected your CPU, your hard drive, your memory, your processor from a set that was predefined for that particular model of laptop, for example, right? For that particular form factor or screen size or motherboard you're interested in. Shared assets, again, when you order a computer, they don't go out and build a special RAM chip for it. They go and grab a pre-existing part that's supported in that model. The number of variants is astronomical, but we still can support this because they're formed by making a set of successive constrained choices from a set of shared assets. In the same way, we have specialized and standardized software. Software development has seen a history that's not really that different from that of producing physical goods, and highly connected to that of physical goods. Early software products were handcrafted for specific hardware and a specific purpose, and sold bundled with that hardware in small numbers. However, software production became increasingly challenging and expensive with the demand for more and more complex software and more usage scenarios that we had to meet. Software producers attempted the strategy then that's not unlike that of mass production, of standardization. Instead of redeveloping operating systems or compilers or tools again and again and again, the software industry agreed on standard platforms, right? And this eventually led to the production of software that you'd go and purchase off of the store shelf, or now that you go and download somewhere, that were deployed in scale and could be installed on millions of different Windows or Mac or Linux machines. Developing a separate word processing or database or accounting software for every company is a ridiculous idea. It'd be expensive and error prone. Buying a standardized and established software solution, go and buy Microsoft Office or Excel, right? Instead of building your own spreadsheet, that makes complete sense. And for most companies, off-the-shelf software is the sensible choice. However, much like mass production provides standardized goods that satisfy the needs of most customers at the cost of not supporting individualism or rare corner cases, likewise, standard off-the-shelf software tries to satisfy the needs of most customers, which leads almost automatically to this kind of situation in which customers are missing certain functionality they want or overwhelmed with functionality that they don't actually need. Like, again, if you think about Excel, do you touch 85% of what's in there? Probably not. But it's there anyway. And would you get a better experience if it didn't have that? Possibly. It might be faster, more intuitive, more reliable if we didn't have those additional features. It's often this generality that makes software complex, hard to use, slow, and buggy. While standardization is important, while it empowered the software industry to substantially scale development and provide affordable software to a broader market, it still left certain types of users out and resulted in software that is bloated, that doesn't exactly meet the needs that you might have, right? And so especially for resource-constrained or energy-constrained environments, like mobile platforms or embedded systems or IoT devices, these kind of bloated one-size-fits-all solutions don't necessarily work, which means that a lot of software is still written from scratch, even though it may be similar to existing products. For example, Oracle might have went out and bought a new database company to perform data management for embedded systems instead of trying to make their own database work on embedded software, right? Again, specific requirements and market segments are typically not well addressed by off-the-shelf software. And so customized solutions or customized variants of the same basic idea, the same functionality are often needed, right? So for example, we might want to individualize a software based on the requirements of a particular customer or particular user interfaces, their desired particular algorithms that we want. We might need to design for particular pieces of hardware, like robots with a particular set of sensors, LiDAR units, radars, cameras, and so on, or different sets of actuators, different types of arms and motors and wheels, right? Or customized software for different hardware devices or different resource restrictions to meet within the requirements of a particular battery, to particular speed or memory that we require, right? Or to meet particular product quality needs of the customers, like certain levels of usability or maintenance effort. Okay. Now, a core challenge, though, when you try to start to customize software, is that software now grows in complexity over both time and space. And what do I mean by this? Well, we start with our first core version here, right? And we make revisions to that code base over time. Right? Now then, if we're Volvo, we go in and start adding variants to our truck model that requires software support. One way to do this is something that's called clone and own, and we'll cover that idea in more detail later, but the basic idea in clone and own is we take a snapshot from our master branch, and we split off, and we start making new changes to this second branch, and then the second branch is our new customized variant, right? And we keep doing this, and over time we might branch off again to create a new variant, and it has its own version history over time as we revise that variant, right? And each time we do this, each of these starts their own timeline where they now evolve, and you can see then why this can get complex quickly. We look back at that exponential curve from Google, right? And as we made changes to the software, those changes add up and they increase complexity. And now we're not just doing this for our core product, we're doing this for all these different variants as well, and they have their own evolutionary history, diverging further and further apart over time. So now you can see that complexity does not just grow over time, but also in space. It's a multiplicative effect from each variant we introduce. And variability adds essential complexity. Let's say you've developed one successful turbofan engine and you get new customers. You have small airplanes or large airplanes or helicopters or jet planes or propeller-based planes, and all have the very same basic turbine engine design. So you get variants. Turbofan, turboshaft, turboprop, etc., right? Supporting a greater and greater number of hardware models. And when you develop this set of products, you deal with variations in the requirements and the architecture, the implementation, the testing, and the maintenance. Code that implements many variants is inherently more complex than code implementing a single product. And the same applies across every phase, not just implementation, but requirements grow more complex as we have more variants to support. The architecture grows more complex to support these different variations. Testing grows more complex because you need to make sure that the feature interactions work for each variant, not just for one core product. And maintenance grows more complicated over time because now you have to make sure that you maintain all these different efforts, that you handle the differences between each of those variants, and that when you go and fix a bug in one, that you fix that bug in all of them, which can grow really complex as these differ in scope and functionality. Right? So to give an example, we can look at 5 open source software ecosystems. You can think of these generally as individual systems. One unit, install, run, but they're all highly variable and they can be greatly customized to the point where they're unique to individual users. And your configuration, your custom version is not the same as everyone else's. Right, so we have 5 products here. Ecos is an OS for embedded systems. The Linux kernel is a general purpose set of core libraries needed for a Linux-based operating system. Eclipse is an integrated development environment for a number of programming languages. Debian is a complete Linux distribution, a complete operating system built on the Linux kernel, but with its own unique additions for desktops and servers. And Android, of course, is the most popular mobile device operating system, right? So how can these be customized? Well, Ecos and the Linux kernel are customized by setting configuration options. Eclipse is customized through add-on bundles. And these support new languages or new development features in your IDE, adding testing and debugging, refactoring options, etc. Debian can be customized by the packages you choose to install on it, changing core components of the operating system, swapping elements of the underlying OS with other compatible options, which can add or replace functionality. And Android can be customized by the apps that you have installed who can register to respond to particular system events. I don't necessarily mean that you have more programs running, but you can change the fundamental experience in Android. The apps installed determine how events are handled, which app makes a phone call, which opens an email, which reads downloaded files. And apps change the UI actively and create a customized experience for each user built on roughly the same core. And each of those has vast levels of variability. Just look at the number of variables, number of options we can choose from. This isn't the number of different customized versions necessarily, but the options to choose from. Just the sheer number of variables is huge, in the thousands. Look at Android, right? This is actually a somewhat old stat, but over 3.3 million different apps you can install, right? The numbers here of different configuration options you can choose are insane. More in many cases than the number of atoms in the universe, right? 2 to the 32 is the number of atoms in the universe. Well, there's more ways that you can customize Android than there are atoms in the universe, right? And that level of scope is insane. Each ecosystem uses different strategies and techniques to implement and control variability. A variability mechanism is an implementation technique to delay design decisions about functionalities and qualities of a system so that we can control how it varies, to flexibly adapt software to the user requirements at later stages, like the build, startup, or runtime. Variation points are introduced into your software platform using an architecture that supports variability in the code, that supports plugging in different options at various points. Right? So variability mechanisms are used to implement variation points, which are locations where variability can occur. Variation points are bound with concrete variants, concrete options we can choose, which are either known ahead of time in a closed platform or unknown in an open platform like Android during platform development, right? You plan to have different things that can attach on. For instance, the Linux kernel is a closed platform. There's a known set of configuration options. You set your options and then compile a customized kernel for your needs based on those options. It means you have a known number of variants. It means you can plan for how the Linux kernel can be customized for your particular needs. Now it's open source and things could change, of course, but the code contains all the possible options and we can expect that code and count them. On the other hand, in an open platform like Android, we cannot know all the possible variants, right? Anyone can create a new app and that app can latch on to system events and respond to them. But we can still control variants through defining constraints on these variation points and where we plug in these options. For instance, we could use any number of apps to handle an event like sharing a photo. Anyone can add more options. However, we have a defined point and a defined event, which is sharing a photo. And that gives a way to control how handling is performed, how event handling is performed, and define constraints on the options that are used to handle those types of events, right? And any app that wants to respond to those events has to obey those constraints. Yeah, as someone in the chat mentioned, intense, exactly that, right? Each ecosystem uses different strategies and techniques to control variation. Linux and Ecos use what are called feature models, and we'll talk about those a lot more, but feature models are essentially hierarchical menus of configuration options, right? At this level, you must choose between these options. Once you choose that option, well, here are the options you can choose as a result, constraints added at each level. Feature models abstractly describe and organize the variabilities at a central place. These are input to different configuration tools, which help users in resolving these variabilities and help them in choosing compatible sets of options so that you don't get a version of the Linux kernel that doesn't compile, that doesn't work as you'd expect. The constraints imposed restrict the valid combinations and the values we can choose from for those features based on decisions that are made higher up in that hierarchy. Debian and Eclipse use package management systems with defined manifests. These manifest files give us metadata about the options that we're choosing. They let you add variation in a flexible, extendable manner. You can define new packages in Debian, for instance, but still enable centralized collection and configuration of options using the metadata from these manifests. The manifests have to adhere to a predefined schema. This could be a grammar for a textual manifest or an XML schema for an XML-based manifest or schema imposed on a JSON manifest and so on. And that contains information like the version information, the dependencies, and categorization information. Android allows more freedom than any of those through what are called service-oriented apps, which provide interfaces and a list of required capabilities which are looked up and bound at runtime to compatible apps, which the user can then select their preferred option from. We don't care about the internals of the apps, what's going on inside them, what they are, how they work, but we define a common interface and requirements and offer hooks for that app to attach to. At runtime, then we can call the interface and it delegates to the correct app. Right? So whenever you're managing variability, there is an inevitable friction between managing variability and encouraging free variability. Managing allows control of the scope of the system and limits to the complexity. It lets you eliminate variants that aren't needed, and it gives you control over development and evolution of a system over time. However, encouragement is also good as well because that unleashes community innovation. That lets the system, the ecosystem you design, do more than you ever intended from the start and grow vastly in its functionality from the start. It enables far richer experiences and far more customization. The cost is that you let the community decide the scope now, right? Both sides have their merits, and it's not really one or the other. It's a matter of a spectrum where you choose the right options for the system you're building. Control is good, but encouragement is also good. Enabling competition. And the open marketplace in Android is what makes Android so compelling and so powerful of an ecosystem. Now, there's a lot of options we'll cover throughout the class to help manage and help control variability. So what we're going to do now is we're going to take another break. Let's take slightly longer. Let's take a 15-minute break this time. We'll come back at 40 after, and we will finish up. Cool. And then again, if there's questions, feel free to ask them in the chat, and I'll get to them in the meantime. But yeah, let's go ahead and take a 14-minute break. Yeah, come back at 40 after. All right, let's get back into it for one more segment today. And so let's start to talk about software product lines and what they are. All right, so let's say we want to customize our software. How do we do this? Essentially, there are three options. You can build each version completely independently, start from scratch, or selectively reuse code and develop independently. This can be good, right? So starting from scratch, developing independently, and maybe selectively reusing some code, that can be good, but it's obviously very expensive and requires great effort, right? The second potential approach is this clone and own, which I mentioned a little earlier, where you take your existing code and you split off a new branch and you start making your own changes to that split version, right? And again, that can be very useful. The third approach, which is the basis of software product lines, is to use shared assets, to have a core code base with variation points where you choose from elements that you've built once as part of those assets and reuse those and bring those into play. Right? So the central idea of software product lines is that instead of developing software systems from scratch, that they should be constructed from reusable parts. Instead of composing a system always in the same way, it should be tailored to the requirements of the customer, where customers can select from a large space of configuration options. The software product line approach provides a form of mass customization by constructing individual solutions based on the portfolio of reusable software components, essentially blocks of functionality that you slot into place at these variation points. Those shared assets I keep mentioning, where an asset can be code components, it can be a class, it can be an architectural element of your system, a subsystem, an API, a UI element, images, even other resources. Software product lines introduce individualism into software production, but still retain the benefits of mass production, and that huge domain and market segments can be covered, right? You're not by hand customizing a system for one customer, you're letting them choose a set of configuration options to get a nice lean version of the system that meets their particular needs. It also avoids the exponential explosion in time and space, as we don't manage entire clones, like in the clone and own approach, where we have now, instead of one core timeline of software changes, we have 3 core timelines. As we don't in the product line, we don't have to manage entire clones, but rather this one portfolio of assets and then variation points. And then we produce the software from these assets that live in one code base with one timeline of changes. Ideally, based on a set of reusable parts, a software manufacturer could generate a software product based on the requirements of a certain customer. So the concept of a feature is central to achieve this level of automation. Features are used to distinguish the products of a product line. For example, one text editor might provide a spell checking feature while another doesn't. Or in a database system A provides multi-user support and version B doesn't. Or email client A supports IMAP and POP3 protocols, while client B only supports POP3, and so on. So as a result, we tend to organize and structure the whole product line process, as well as all the software artifacts involved, in terms of the features, right? And how those features can vary based on different options we choose. And we reason about variability by discussing how to control, implement, and verify the interaction between different features. That way, it's easy to trace the requirements of a customer to the software artifacts that provide the corresponding functionality to meet those features. right? We make features explicit in the requirements, the design, the code, the testing, and so on across the entire life cycle of the system. So an example of a software product line that you interact with daily is an operating system. Almost every operating system an operating system is there to mediate between different hardware and pieces of software, right? And modern operating systems have to run on a variety of different hardware platforms, and they have to serve the requirements of all sorts of different applications and customers. So for example, the Linux kernel can run on a huge variety of different platforms, all the way from an embedded computer the size of your thumbnail up to the servers that power most of most internet applications, right? The Linux kernel can run on everything from embedded and mobile devices, it's the core of Android, to desktop systems, to large-scale server applications, and supports a huge portfolio of different application scenarios, from control applications to office software to games to high-performance computing and server software. And to do all of this, the Linux kernel has to be highly customizable. And it is. So clearly, there cannot be a single operating system that efficiently supports all kinds of different platforms and all application scenarios. Instead, modern operating systems are configurable. So the Linux kernel has over 8 million lines of code. It supports over 22 different hardware architectures like ARM, x86, PowerPC, RISC, and so on. Has over 13,000 configuration options, over 13,000 features that we reason about. Most source code in Linux is optional. When you compile the kernel version for your particular scenario, you're not working with 8 million lines of source code. You're working with a lean compiled version that matches the options that you set. What you get when it's running and available depends on the choices you make when you select those configuration options. Right, so here we have a screenshot of the Linux configuration tool, which is called kconfig, and this can be used to tailor the Linux kernel for very specialized uses, right? And so what you see here are a bunch of checkboxes, basically indicating what options you want to choose for different features. Kconfig makes the Linux kernel highly modular and highly customizable. You don't need to be an expert in this particular tool. I'm not going to ask you to run this tool and choose different options, but what you can see here is it shows the kind of customization we're talking about. You can select which features you need for your particular version, your particular installation of the Linux kernel. What processor family you're supporting, which hardware architecture, which hardware features are required. And under the hood, then, this allows you to compile a custom version of the Linux kernel, omitting the source code that you don't need, leaving out unnecessary features, leaving out code for options you didn't choose, which would only lead to potential bugs and slowdown and bloating if you had to include all of that in your final application, and could potentially lead to incompatibilities or unforeseen feature interactions based on the options you chose. Instead, we discard everything we don't need, and we get a version of Linux compiled for our particular usage scenario, right? So in Linux, customization is controlled through a feature model, the type of model we mentioned earlier. The feature model imposes a hierarchy over customization, imposing constraints in the combinations of choices we're allowed to make. The configuration options are the features of this model, right? So defined constraints are used to prevent illegal combinations of features. So first we can see how this is defined in the code, right? So within the code, we have these if-def statements, right? These are our annotations, right? These are not really source code, but what these are is these are picked up by the compiler, and they look at the set of options we're chosen. And if we choose that option, that includes that code. And if we don't, it isn't included. So if we say we want this config ACPI option, this particular method call will be included in our code when we go to compile our particular version of the Linux kernel. If we don't choose this feature, then it won't be there in our code, and this call will never be made, right? So this is an option we can enable, this config ACPI. ACPI allows the operating system to control power management as opposed to controlling it at the BIOS level. In the code, we can check where that option is enabled by, we can select that, and then the compiler we'll look at what we selected when it goes to compile and look for these if-def statements. And if we selected this, if this is true, we will include this call. And if we don't, we'll ignore it, right? So this is a feature in C and C++, but there's also similar notions for things like Java using annotations. If we've chosen this option, we'll call this method and then continue execution. If not, we'll skip this step when we compile. And so our compiled version won't include that method call. Right. This type of customization is a cornerstone of product lines. We select options and we get a unique build tailored specifically to those options. Now, feature interactions can lead to errors in software. If we choose the wrong options, then problems will emerge because those options aren't necessarily compatible with each other. And there are many choices that are fundamentally incompatible with each other in any system. So the feature model uses user-defined or inferred constraints to prevent those kind of errors. For example, we can take a look at this code here. So first, the entire block of code is compiled only if this ash option is true. So we see this if-def ash. So if this ash option is true, we'll include this block of code. If it's not, nothing in here gets included. This is looking to see if we're using the ash shell, which is different from bash or any of those. So if we're using ash instead of the more common bash, this piece of code will be included. Within this, we check if we're using this NAMU hardware architecture. And if we are, if both are enabled, we have a problem, right? There's an error that will come out if you select both of those, right? Because this shell won't run this particular hardware platform, right? So we have a constraint. There's an error if this constraint is true of ash and NAMU, right? So we have our first feature in compatibility. Now we'll continue. Next, we have some code that we include if the editing option is enabled, right? If the editing option is enabled, well, then we'll include this init method, right? In this method, we have this max length variable is 1 times, and then if this option editing max len is enabled, it's 1 times the variable editing max len, right? We're going to have a problem if this option is not enabled, right? If this option is not enabled, we have an incomplete line, int max length equals 1 times, right? Nothing is left because we didn't choose this option, right? So there's a parser error if we don't include that option. So if ash and editing are true, editing max length needs to be true to compile successfully. If it's not, we're going to get a parser error. Does that make sense, right? Feel free to ask questions if anything's not clear. Right. So here's a problem. If this variable is not, if this option is not chosen, our code's not going to compile at all, right? So we can avert both of these types of errors by defining constraints in our feature model. In our feature model, what we can do is we can say that we require ash and not NAMU, right? So NAMU can't be true if we're using ash. Or we could have a constraint that says ash and editing max length must be all true together, right? And if we have those, then we can avert these two particular errors. So what we need to do is when we set up our feature model, you need to make sure you define your constraints carefully. And we're going to talk about this in way more detail in the next few classes. So you don't need to be an expert on this yet, but this gives you an idea of how we can control variability in our system by applying constraints and what kind of feature combinations you can choose. Right. When you're choosing between developing individual software products from scratch or developing standardized one-size-fits-all products, software product lines give several distinct benefits. First of all, these are tailor-made. A product line approach facilitates tailoring products to individual customers. Instead of providing a standardized product or a small set of pre-configured products, you can produce a whole set of differently tailored products from pre-made components. It gives you reduced costs when providing each customer their desired solution. You don't need to pay the cost of designing and developing every product from scratch. Instead, you develop reusable parts that can be combined in different ways. This development cost per product per customer can be reduced to selecting which parts to combine and potentially adding some missing features the customers might want, and to testing the resulting product. You get fast startup when creating a new variant because, well, you've already got all these assets. All you need to do is combine them in a new and interesting way, right? You get improved quality. Mass production has improved quality because standardized parts can be checked systematically and tested in many products. Standardized software offers similar benefits compared to software developed individually from scratch, but software product lines offer a compromise in that different products are constructed from standardized parts. Though not every combination is going to be used by millions of customers, parts can be checked in isolation to some degree, and parts are reused and tested in multiple products. Parts that are used frequently lead to stable, lean, and more reliable code. And then finally, you get reduced time to market. While standard software is readily available, handcrafted software requires significant cost and time before it can be released. If a customer selects only from predefined configuration options that map to existing components in your asset portfolio, then you can quickly produce the requested software by assembling the existing corresponding parts. Even if a feature requests functionality that's not been prepared, building a new product on top of existing well-designed and reusable parts is much faster than developing entirely from scratch. So a well-designed platform that can be extended for new products gives you the ability to quickly react to market changes more so than the individual development or standardized software can. Product lines have grown more and more common in modern systems, and many modern systems use similar approaches to manage configuration, complexity, and variability. And these approaches have led to major successes. We'll look at a bunch of case examples throughout this entire study period. And I mentioned a couple like Linux and Cummins and Android and Eclipse and so on, but many companies employ product lines. Some well-known examples are things like Boeing or Ericsson or NASA or Volvo, right? Any of those, Hewlett-Packard with the printers. And there's a lot of success stories at a website called SPLC.net. Some of those are a little older than others, but it's a good place to look for just some examples of how these product lines have benefited in practice. But just to give a concrete example, we can look at a different company before, look at Hewlett-Packard. They have a product line approach developing printer firmware. Their product line consists of 2,000 features supporting hundreds of printers. And when they move to a product line approach, they can produce products with a quarter of the staff in a third of the time and with a 1/25th of the number of bugs of earlier products, right? And they can support hundreds of different printers from a core set of code assets. Right, so that's about it for today. Basically, modern software is complex, right? And when we talk about complexity, what we're really talking about is variability, which is the ability to change and customize software to deliver variants to new users, evolve the software over time, and changeability and maintainability, the ability to add new features, new functionality, while ensuring the existing code still works as we would expect. Software must evolve to remain useful over time. That's just a fact. But evolution is difficult. It increases complexity, and it makes it harder over time to produce software that works quickly, that's secure, that functions well, that's fast, any of that. Product lines are systems that are designed to handle variability and evolution, designed to enable and take advantage of reuse. Next class, we're going to talk about the process of starting to form a product line or a reuse-driven system based on domain and application engineering. In terms of what you should be doing for the class, for homework, plan your team selections, right? Get those sent in by Thursday, 6 to 7 people per team, one email per team with the names of everyone. And let me know if you want to be assigned to a team. In the chat, someone just asked, when will recordings be uploaded? Soon, possibly later today, maybe by tomorrow morning, but there won't be a long lead time before these are up on the website. Just whenever I have a little bit of time to get everything uploaded. Are there any other questions before we finish today? All right, then. Well, feel free to reach out via email. And otherwise, we'll see you this time on Thursday at 1:15 again. And please get those team selections in. Thanks a lot.